So I was suspicious of this number because it seems a little small, the number 2 3/4. So I was suspicious of my fraction addition, but that's not where it is. The error is up here. The height of the rectangle A4 is not 2. The height of the rectangle A4 is 2 squared, which is 4. This number is 4. So this number is 2. So this is actually 3 3/4, which would be the same as 15/4, right? 15/4? Yeah, 15/4. So this number, 3 3/4. I actually didn't like this number by instinct, and then when I did the next one, the next number should be smaller, and it wasn't. So anyway, now let's go to n equals 8, now that we've fixed our n equals 4. I've fixed my n equals 4. All right, so here's what we're doing for n equals 8. So what I did was I drew the picture, and I've laid out this chart. So this chart is going to be a handy way for us to keep track of the values that we need to keep track of. So we want to think of the beginning of our interval as being a, and which in this case is 0, and the end of the interval as being b. And we also want to think of all these numbers in between as being x0, x1, x2, etc. So in general, they are x sub I, and that's the x sub I that I have here. All right, other things we want to keep in mind, since the n equals 8, we can figure out the delta x. I mean, we can look at the picture and say the delta x is 1/4. It will not always be that obvious, and it will be useful for us to know that the delta x is always b minus a over n. That just means the length of the interval from a to b divided by the number of rectangles you have. So of course that would be the width of each rectangle. So in this case it's 2 minus 0 over 4, which over 8, which is equal to 1/4. So our delta x equals 1/4 for this problem, for n equals 8, and we're going to do the right-hand sum first. Okay, so what we're going to do is we're going to first look at I. Now, you might be familiar with I as square root of -1. In calculus, often the I is not representing square root of -1. You have to look at the context. Here, the I is the index. So it's an index variable. It just says which number triangle am I on, or which number rectangle am I on. All right, so the I's are going to go with just 1, 2, 3, 4, 5, 6, 7, 8. They start at 1 and end at 8 because I'm looking at the right-hand rectangle. So I'm going to start with x sub 1 and end with x sub 8. All right, that's b is going to be x sub 8. When I do the left-hand sum, I'm going to start with x sub 0 and end with x sub 7. So that's essentially the difference between the right-hand sum and the left-hand sum. All right, now I need to look at what the x sub i's are for each of my index variables I. So x, just by looking at the graph, x sub 1 is 1/4, x sub 2 is 1/2, x sub 3 is 3/4. So, and by the way, in terms of, computationally, where are these x sub i's coming from? Each x sub I is the preceding x sub I plus delta x, right? There's a delta x difference between each of them. So we could say, for example, that x sub I is equal to x sub 0 plus n delta x. So that's not going to be an extremely important formula to us, kind of pretty much ever. However, people who are interested in, trying to set this up, a computer program to do this, computer enthusiasts might look at this and say, oh, you know what? I could have a computer program. I could write a program to do these sums using arrays or something like that. All right, I don't know what terminology the kids use today in their computer programming world. We used to call them arrays. All right, anyway, 3/4, 1, 5/4, 3/2, 7/4, and 2. The x sub i's form a sequence whose initial value is 0, but I'm not including it, and whose common difference is 1/4. So you can think of the x sub i's being an arithmetic sequence. However, there are going to be certain problems where they are not. But when we do most of these, these are a nice arithmetic sequence because the delta x is constantly 1/4. Okay, now I need to go through and find out the f of x sub i's. F of x sub I is just x squared, which I didn't write up here. There's f of x equals x squared. And I was also going to mention that I translated the names of the variables. We were calling this v of t equals t squared in our velocity context. I want to generalize the context. So I'm just going to say this is any function f, and I'm going to use the traditional x variable for the horizontal asymptote, the horizontal axis. So f of x equals x squared instead of v of t equals t squared. All right, that's going to give us sort of our common terminology for these things. So my f of x sub i's are going to be x squared for each x sub I. So 1/4 squared is 1/16, 1/2 squared is 1/4, 3/4 squared is 9/16, 1 squared is 1, 5 squared is 25/16, 3/2 squared is 9/4, 7/4 squared is 49/16, and 2 squared is 4. Now, look, of course, we could do all this on the calculator, but it's really good for you to practice using fractions and using your head, all right, to do these things. All right, so even though, arguably, I'm an argument against that since I make mistakes that way, but if you continually check your work, it's a good skill to have. Now, we know that delta x is 1/4, and for this problem, the delta x, remember, delta x is the width of these rectangles. That delta x is constantly 1/4, so for every rectangle, the delta x is 1/4. So I like to write that in as a column in my table, and you'll see why. So then, when I go to find the areas, well, the f of x sub I is the height of the rectangle. Right? The f of x sub I is the height. So let me see if I can scrawl that in here. F of x sub I is the height, and delta x is the width of the rectangle. So the area of every rectangle is f of x sub I delta x, which is an important formula that you want to keep your eye on, because we're going to develop that a lot. All right, so if I want to get each area of each rectangle, I just multiply. 1/16 times 1/4 is 1/64. 1/4 times 1/4 is 1/16. 9/16 times 1/4, 9/64. 1/4 times 1/4, 1/4. 25/16 times 1/4, 25/64. 9/4 times 1/4 is 9/16. 49/16 times 1/4 is 49/64, and 4 times 1/4 is 1. Those are a sub i's. Now I want to add them up. I just add them up. That's the next step. And then I've got my area estimate. This is doing a Riemann sum, a right-hand sum with 8 rectangles on this function on the interval 0 to 2. All right, so here are some cool things I can write. The area under the curve is approximately equal to the sum from I equals 1 to 8 of a sub I, right? This is a summation notation, so you should be familiar with this from pre-calculus. So if I do the sum from I equals 1 to 8 of a sub I, that just means add up all these a sub i's. This is a1, a2, a3, a4, etc. All right? So another way I can look at that is the sum from I equals 1 to 8 of f of x sub I delta x. And this is one you really want to keep your eye on. That the sum is really, because this is where we can use the limit and get infinitely many rectangles. The sum from I equals 1 to 8 of f of x sub I delta x gives an approximation. But if I could somehow do the sum from I equals 1 to infinity, then it would not be an approximation anymore. It would be exact. But how am I going to do that? That's absurd. All right. Now, what I have to do here is just add all these up. When I did this as sort of scratch work, what I did was like you can do certain tricks with this, like put all the 64ths together. So I have 1/64, 9/64, 25/64, 49/64. Add all that up together and you get 84/64. So I just took the ones with the common denominators first. And I noticed cool patterns like 1, 9, 25, 49. It's the sequence of the squares of the odd numbers. Think about that while you're trying to fall asleep tonight. Don't count sheep. Try to figure out why that pattern exists. All right, I got 1/16 and I got 9/16, so that gives me 10/16. And then I only have 1/1/4, and I have a 1. So then I said, okay, look, 84/64 conveniently reduces to 21/16, and then my 10, and so my natural common denominator here is going to be 16ths. And then, so I call this 4/16, and this one 16/16. And that's just adding up the fractions. You can do that however you want. I'm just putting it as scratch work over here. And I came up with a total of 51/16, also known as 3 3/16. Yeah. All right. That's my right-hand sum, and we'll talk about how to, so you should actually go ahead and do the left-hand sum. I'm going to do the left-hand sum. So let's pull out of the videos. You do the left-hand sum with n equals 8. I'm going to do the left-hand sum with n equals 8, and we'll compare notes at the end. So all you're going to change is instead of I going from 1 to 8, I is going to go from 0 to 7, because we're going to use the rectangles on this side instead of on this side. Okay, so we're going to do 0 to 7, means we're still going to use all these values, but we're also going to add in the 0 value. So what will your table look like, and what will your sum be?